Have you ever stopped to think about how the exact same unseen force that, causes a dropped basketball to slam into the gym floor is the very same force guiding multi-billion-dollar spacecraft through the dark void of space? Oh, and it also controls the crashing ocean tides. It honestly seems like magic, right? But nope, it's just physics. Welcome to this explainer. Today we are unlocking the secrets of the cosmos by diving deep into Newtonian gravitational laws.
Okay, let's jump right into our roadmap for today. We're going from falling apples to deep space. We'll start with Kepler's what and Newton's why, move right into inertia and unseen forces, and then unpack mass, force, and reactions. After that, we'll look at the glue of the universe, see how we're navigating the solar system, and finally, we'll bring it all back down to Earth with the pull of the tides.
Section 1. Kepler's what, Newton's why, the orbital mystery.
So for a really long time, the movement of the planets just completely baffled early scientists. They'd look up at the night sky and scratch their heads. Our story really kicks off with two brilliant guys. First up is Johannes Kepler. Kepler was the man who figured out the what of planetary movement. He observed that planets don't actually move in perfect circles like people thought. They have elliptical or, kind of oval-shaped orbits. He also noticed they change speeds depending on how close they are to the sun. But here's the kicker. Kepler had absolutely no idea why they did this. It wasn't until the English scientist Isaac Newton came along that we finally solved the why.
Sir Isaac Newton realized that the unknown force directing all this crazy celestial traffic was gravity. He figured out that gravity is essentially a force pulling objects toward each other. And this invisible pull, it's exactly what determines those specific oval shapes of the orbits and those changing speeds Kepler saw. Basically, Newton wrote the rule book for the mechanics of our universe.
Section 2. Inertia and unseen forces. Newton's first law.
All right, let's define a totally crucial piece of our vocabulary here, inertia. Simply put, inertia is a property of matter that keeps it in its constant state until an outside force acts on it. You can kind of think of it as the universe's tendency to be, well, a little stubborn. Objects that are sitting still, they really want to stay sitting still. And objects that are moving, they really want to just keep moving in a perfectly straight line forever unless something rudely interrupts them.
Now think about that interruption to inertia. Gravity acts as that outside force. Like if you throw a baseball, inertia wants it to go straight out into space, but Earth's gravity pulls it down, bending its path into a curved arc. Orbiting planets act the exact same way. The Earth's inertia wants to launch it straight out of the solar system, but the sun's massive gravity keeps pulling it inward. So the combination of that forward motion and that inward pull, that creates the continuous loop, the orbit we call a year.
Section 3. Mass, force, and reactions. Newton's second and third laws.
Let's explore how the physical size, or mass, of an object totally changes the rules of the game. Newton's second law is something you've probably experienced a million times. It states that the force acting on an object is directly related to its mass and its acceleration. Imagine pushing a car. If it's a tiny toy car, a little flick of your finger sends it flying, right? But a real car has a massive amount of mass, so it takes a massive amount of force to get it moving. Out in space, this means scientists can precisely predict how a planet or a space probe will move as long as they know its mass and the gravity pulling on it.
Okay, quick question for you. How does the simple, ordinary book, just sitting totally, completely still on a desk, apply force? It feels like a trick question, I know. It's just sitting there, but physics tells us there's a whole lot happening just beneath the surface.
And this brilliantly illustrates Newton's third law. For every action, there is an equal and opposite reaction. Think about those desk toys with the metal balls transferring energy back and forth. With our book on the table, Earth's gravity is pulling the book down, meaning the book applies a downward force on the table. But, and here's the cool part, the table is applying an exact, equal upward force back onto the book to hold it up. No way, right? But it's true, and this happens in space too. The sun pulls on the Earth, but the Earth actually pulls back on the sun with the exact same amount of force. The sun just doesn't visibly move much because, well, it's unimaginably huge.
Section 4. The glue of the universe. Law of gravitation. Now that we've got the basic laws of motion down, let's zoom way out. Let's shift our scale from everyday earthbound stuff to the vast cosmic scale. Newton combined all these ideas into his law of universal gravitation, which has 3 core rules that govern absolutely everything, literally everything from tiny pebbles to massive galaxies. Number 1, every single mass attracts other masses. Number 2, a greater mass equals a stronger gravitational attraction. And number 3, a closer distance equals a stronger attraction. It's a beautifully simple set of rules for a ridiculously complex universe.
But to make the math actually work on paper, Newton needed a specific mathematical value to tie the whole shebang together. This is known as the gravitational constant, or big G. You can think of this constant as the invisible glue that holds the entire universe together. It sets the baseline strength for how mass interacts with other mass everywhere.
And with this math, scientists basically unlock a superpower. I mean it. They can actually calculate the mass of far-off, totally unreachable planets and stars just by watching how fast they orbit each other and measuring the distance between them. How cool is that?
Section 5. Navigating the solar system. Gravity in action.
So these laws were written hundreds of years ago, but they are absolutely crucial to what modern mission control teams rely on every single day. One of the most amazing applications of this physics is the gravitational slingshot. Spacecraft can't carry endless fuel, so scientists use the planets themselves to get around. Step 1, a space probe intentionally flies super close to a massive planet. Step 2, that planet's intense gravity grabs the probe, exerting a massive pull. And step 3, the probe speeds up immensely, but the angle is calculated so perfectly that instead of falling into orbit, the probe just slingshots right past, basically stealing a tiny bit of the planet's momentum to hurtle way deeper into space.
Massive gas giants like Jupiter are the ultimate interplanetary boost pads for these slingshot maneuvers. But gravity helps us navigate the dark in other ways too. Remember earlier when we said objects pull on each other? Well, by observing tiny, unexplained gravitational wobbles in the orbit of Uranus, scientists deduced that another giant planet had to be out there pulling on it. And actually, scratch that. It's not just a theory. That is exactly how Neptune was discovered, completely through math before anyone even saw it through a telescope.
Section 6. The pull of the tides. Gravity on Earth. We've spent a lot of time out in deep space, so let's bring the narrative back down to Earth. Let's see how this massive cosmic dance builds into something you can witness on literally any trip to the beach. You see, the Earth, the Moon, and the Sun are locked in a constant gravitational tug-of-war. The Moon's gravity physically reaches out and pulls on Earth's oceans, stretching the water towards it and creating our high and low tides. The Sun does this too, but because it's so much farther away, its effect is a lot weaker than the Moon's, even though the Sun is way more massive.
Now, this cosmic tug-of-war creates two distinct types of tides. Check out the spring tide, which gives us extreme highs and big crashing waves. This happens during a full or new moon, when the Sun, Earth, and Moon line up perfectly, combining their gravitational pulls. Then we have a neap tide, which is way calmer, with a lot less difference between high and low water. This happens when the Sun and the Moon are at a 90-degree angle to the Earth, so they're essentially pulling the oceans in competing directions and kind of canceling each other's force out.
So we've seen how gravity dictates the orbits of planets, lets us slingshot spacecraft, and even pulls the very water on our shores. And it brings up a truly staggering realization. What would happen to our entire solar system if that gravitational constant suddenly changed? Even a tiny fraction of a difference in that universal glue could send the planets flying off into the void or crashing straight into the Sun. It really leaves you marveling at the fact that the exact same unseen force holding you in your chair right now is the very thing preventing the whole universe from flying apart. Thanks for joining me on this explainer. Keep wondering, and I'll see you next time.